Okay, today's lesson we are discussing gases, and particularly the gases in our atmosphere. Our atmosphere is containing 78% nitrogen, 21% oxygen, 0.9% argon, and less than 1% carbon dioxide, roughly 280 parts per million, and recently up to 350 parts per million. What do we know about gases? Gases are completely mobile fluids, that is, that they fill any container they're put into, because the molecules are in a state of constant motion. They have a high level of kinetic energy by comparison to liquids or solids. In a solid, the molecules or atoms are all touching and they're just vibrating in place. In liquids, they have more mobility because they will slide one over the other and roll around, but they tend to stay in the same position, whereas with a gas, the molecules are moving around so rapidly that they bump into each other and they fly a fairly long distance before they bump into something else. As it turns out, gases only occupy about 0.1% of the actual space in the air we breathe. But what they do is because of their rapid motions, they exert a pressure by transfer of momentum. So for example, if you were to throw a tennis ball against the door, when the tennis ball hits the door, it would reverse direction and it would transfer some momentum to the door. Now, if you could imagine that experiment being scaled up so that 1,000 tennis balls are hitting the door at the same time, you could understand that the amount of pressure that was exerted by the bouncing of the tennis balls would be 1,000 times higher, and so on, until you had trillions of tennis balls hitting the door so that the door would literally fly off its hinges. Well, in the case of gases, they're not tennis balls, but very, very tiny molecules, and that is how gases exert pressure. Why don't we feel the pressure at the surface of the Earth? Because we have the same pressure within our bodies, equalized on the outside. However, if there is a pressure difference, then you see how the pressure can exert a force. We can see that when a vacuum cleaner is turned on, it creates a flow of air out the exhaust of the vacuum cleaner, so the air molecules that are now given more space to move will follow each other into the tube of the vacuum cleaner. So in actual fact, the removal of air molecules from a certain area of the volume will cause the other molecules to rush in because they have more room to move before they collide with something else. So that's how a vacuum cleaner works. Anyway, gas molecules mix together perfectly. For example, liquid, gasoline, and water don't mix, so they don't really form an explosive mixture. If you, and I wouldn't recommend you did this, but if you were to drop a match into a bucket of gasoline, if the gasoline had no vapor above its surface, the match would go out. On the other hand, when you have vapors mixed with gasoline, vapors of oxygen or air mixed with gasoline, it forms an explosive mixture. Gases are compressible, unlike liquids, which exhibit very little compressibility. And this is by virtue of the fact that there are large spaces between gas molecules, so there's lots of room to compress the gas. Pressure is measured in pascals, a unit defined as a force of 1 Newton applied to an area of 1 meter squared. So we see here force over area is known as pressure. 1 Newton, which is roughly the weight of an apple in Earth gravity, distributed over an area of 1 meter, gives you an idea of how small of a unit of pressure the Pascal is. Atmospheric pressure, which is exerted at the bottom of the ocean of air we call our atmosphere, is roughly 101,325 pascals. So we have a layer of air above the Earth, roughly 100 miles thick. Of course, it gets thicker and thicker as you get closer to the surface of the Earth. Really, 90% of the atmosphere is below an altitude of 10 miles. We call that the troposphere. And most satellites are placed in orbit some 100 miles up because the air is so thin at that point that it doesn't exert any sort of friction on the flight of the satellite. So there are a few things we should memorize regarding expressions of pressure. First one is 1 atmosphere. It equals 760 millimeters of mercury. What does this mean? If you were to take a glass column closed on one end and fill it with liquid mercury and then invert it into a dish of mercury, the mercury would stay up inside the column, but it would not climb higher than 760 millimeters, about 76 centimeters, because that's the pressure that the atmosphere is able to exert. If you were to do the same thing with a column of water, you'd be able to get about a 32-foot column of water. So what is it that keeps the column of mercury or water inside the tube? It's the pressure that it exerts on the liquid that the tube is inverted into. In honor of Evangelista Torricelli, who was the first scientist to conduct an experiment that described air pressure, a 1 millimeter of mercury pressure is also known as the torr. So 1 atmosphere pressure is also equal to 760 torr. It also equals to 101,325 pascals, or 101.325 kilopascals. It also equals 4.7 pounds per square inch, or enough pressure to raise a column of mercury 29.92 inches. We sometimes see this measurement, this unit, used in old barometers to describe low pressure zones and high pressure zones. Typically, low pressure zones are associated with warm, moist air, which is typically associated with stormy weather. And in high pressure zones, the air is very dry, so it tends to have a higher density, and therefore exerts a higher pressure as well. We also see sometimes weathermen have been known to use millibars as a unit of pressure. You'll notice it has the same numbers as the pascal, except the decimals in a different place. So 1,013 millibars is equal to 1 atmospheric pressure, and recently also the SI unit has become the bar. So 1.01 bar is equal to the atmospheric pressure. There are 3 laws we should become familiar with in regard to gas laws. The first is Boyles Law. Boyles Law states that a volume of a fixed quantity of gas maintained at constant temperature is inversely proportional to the pressure. What does that mean? If you double the pressure on the gas will occupy half the volume. If you quadruple the pressure on the gas will occupy 1/4 the volume, and so on. And mathematically stated, pressure times volume is equal to a constant. Charles' law states a similar property of gases, except it has to do with temperature. The volume of a fixed amount of gas maintained at constant pressure is directly proportional to its absolute temperature. And if you were to cool a gas down to absolute zero, in theory it occupies 0 volume. This is if you plot the volume occupied by a gas versus the temperature, you'll see that the volume of the gas decreases and converges to 0 at absolute zero, which is minus 273.15 degrees Celsius. It's also known as 0 Kelvin. Finally, the combined gas law takes these 2 laws along with the amount of moles of the gas into one law, which is probably the only useful one that we have here, because when you don't have any one of the units that we would use in either Boyles Law or Charles' Law, you simply cross them out because they're not there. So the combined gas law is P1V1 over N1T1 is equal to P2V2 over N2T2. Both of these are equal to a constant. This version of the law is great if you have initial conditions and final conditions. If you only have one set of conditions, you can use PV equals nRT, where R is equal to the gas constant, which can vary according to which units of pressure are used. P is for pressure, V is volume, N equals the moles of gas, and temperature has to be in absolute temperature, that is in degrees Kelvin. So if you know the temperature in Celsius, simply add 273.15 degrees to it, and you'll get the Kelvin temperature. So 0 degrees Celsius, the freezing point of water, is equal to 273.15 Kelvin. Here's a problem which I devised to help us understand units. I ask, a penny weighs 2.85 grams and is 19 millimeters in diameter. How many pennies are needed to make a stack that exerts a pressure of 1 atmosphere? We recall that the unit of pressure is the pascal, and that pressure is force over area. Units of force are in newtons. The area is expressed in meters squared. So if we can find the surface area of 1 penny using pi r squared, here it is in centimeters for the radius, and we divide it by 2. Sorry, this is the diameter, divided by 2 gives us the radius squared, times pi gives us an area of 2.83 centimeters squared for a penny. We then convert that mass of the penny into kilograms. We multiply by the acceleration due to gravity so we can get the force converted into newtons. So this is the force exerted by a penny in newtons. This is the area of a penny in meters squared. But notice we divided by 10,000 because there are 10,000 centimeters squared per meter squared. And we get that a penny exerts a pressure of 98.6 pascals. Now, how do we get a stack of pennies that would exert a pressure of 101,325 pascals, which is equal to 1 atmosphere? We divide the atmospheric pressure in pascals by the pressure exerted by 1 penny. Pascals cancel, and we find that it takes a stack of 1,027 pennies to exert a pressure of 1 atmosphere. It's actually 1,028 because you can't get half a penny. So you make a stack of 1,028 pennies to exert a pressure of 1 pascal.